Hello everyone. Our today's topic is GSM frame structure. In the previous lecture, we have studied about GSM technology and also we learned about GSM architecture and we have studied different components of GSM architecture. Since we know that in GSM we use TDMA as multiple access technique, and in TDMA the data transmission is in burst forms. So here data transmission is in burst form. Burst form means the data transmission is not continuous, and in order to transmit the data, we have different data transmission formats. So, in total, we have five different data burst formats. Number one, we have our normal burst. Number two, we have FCCH burst, that is your frequency correction channel. Then, number three, we have SCH Burst, that is your synchronizing channel burst. Number four, we have RACH Burst, that is your random access channel burst. And the last one is your dummy burst. So these are your different data bursts which are used to transmit the data in GSM technology. And in today's lecture, we have to study about all these five different formats. So we will start with normal burst, that is your first one. These different bursts which are used for data transmission, they are basically the categories of time slots which are used by the users to transmit the data. So every time slot may have different fields which are used by the users to transmit the data. So normal burst has different fields. This is field number one. Then you have second field. This is your third field. Then fourth field. After that you have this fifth field, and then you have your sixth field. So there are different fields, and in normal burst you have six different fields. This first field is of 3 bits and it is known as start bits. Then second field is of 58 bits and this is known as your encoded or encrypted data. Then your third field is of 26 bits and this is called as training bits. Then we have fourth field, again it is of 58 bits and this is again your user information or the encrypted data. After this you have another field that is of 3 bits and this is called as stop bits. And the last one is your field which is of 8.25 bits and this is called as guard period. You must be confused with this 8.25 bits, that why it is in fraction. I will explain this later. So when we calculate all these bits from different fields, we get 156.25 bits in total that are transmitted per one time slot. Okay, so here in this burst you have initially 3 bits which are called as start bits, and again you have 3 bits over here which are called as the stop bits. So these 3 start and stop bits, they are basically the ramp up time that is used by this particular burst, or in addition to these guard period bits, this one, these are used to provide sufficient delay in between the frames or in between the time slots in order to avoid the time slots overlapped during the multipath propagation in the TDMA kind of framework. Okay, so these 3 start bits, 3 stop bits along with the 8.25 guard period, they are used to avoid the overlap between the different frames or the different time slots which follow the different propagation paths. So next we have 58 bits. This is the user information or the actual data that user wants to transmit. This can be your voice, and this is the actual data that user wants to transmit. Then you have these 26 bits which are called as the training bits, and these are basically used for the synchronization purpose. And after that you have 58 bits of encrypted data again. So here you see that one 58-bit of encrypted data field and another 58-bit of encrypted data field, and in between these you have these training bits. So training bits, basically these are the synchronization bits, and these actually allow the adaptive equalizer to analyze the characteristics of the channel. For example, if the channel is not good and suppose this field of data it gets distorted, then this field is activated and it allows the adaptive equalizer to analyze the characteristics of the channel, and then the next 58 bit of data is received correctly, because before the decoding of data the channel is analyzed first, whether it is okay kind of channel or it is a channel where we have attenuation. Okay, so this is done by this particular field which is having 26 bits for this purpose. Okay, now this whole time slot, here we have last field as guard period, and it is of 8.28 bits, and basically this is represented here in terms of bits, but this is actually a time delay which is there to keep the two different time slots away from each other, so there should not be an overlap of frames or overlap of time slots. So in total, for the transmission of this particular time slot, we have 0.577 milliseconds of time for its transmission. So this 8.25 is fraction is given in such a way that we have to complete this much of time, and by utilizing these bits, these bits, these bits, these bits, these bits, and also the last field, that is 8.25. So in the last field we can have a guard period of up to 8.25 bits. That means the time taken by these many bits for the transmission, that is the time which is given in its part, that is your guard period. Okay, so next we have other data burst type, that is your FCCH burst. FCCH burst. Before this, I must write here that this is used for both traffic channels as well as dedicated control channels. So here the transmission is forward as well as in the backward direction. And after that we have this FCCH burst, and again this FCCH burst have different fields. Let me draw those fields. So here in this category we have initially 3 bits, and these are called as usual your start bits. The next field is of 142 bits, and this is your field of fixed 142 bits, and here all bits are zeros, so these are all zeros. And then we have 39 bits of next field, and this is your encoded data. And after that you have another field here, that is your 3 bits again, and these 3 bits are your stop bits, and the last one is your 8.25 again, and this is your guard period. Okay, so here what we see that initially we have 3 bits, these are the start bits, again you have stop bits and guard period, that is just to avoid the overlap of different time slots. And here you have the probability of sending data, that is of 39 bits only, and then 142 bits of fixed bit field that contains all zeros, because it is not meant for the data transmission. And this particular category of time slot, it is used in the time slot 0, the initial slot that is used before the actual communication starts, and this is just for the synchronization purpose, and it synchronizes frequency and time. Okay, and it is not actually used for the data transmission or the payload transmission, and basically it is used for transmission of the control messages. control messages on forward link. Okay, that is from the base station to your mobile station. These control messages are sent, and for that purpose we use this type of category, this type of format, that is your FCCH burst. Fine. And next we have to study about SCH burst. In SCH burst we have 6 different fields. So here as usual we have 3 bits, and these are your start bits. Then we have 39 bits, these are your encrypted data. Then we have 64 bits, these are the trailing bits. Next we have again 39 bits, this is again your encrypted data, that is another chunk of data that can be transmitted. After that you have 3 bits, that is called as stop bit field. And then you have finally 8.25 bits, which is your guard period. Okay, and this SCH burst is called as a synchronization channel burst, and it is again used in time slot 0, and it is used for the frequency and time synchronization, frequency and time synchronization. And also this is used for the transmission of control messages on forward link only, control messages on forward link only. So this is again not meant for the data transmission. Basically you can transmit data, that is of 39 bits here and 39 bits here are reserved for the data transmission, but in particular it is used for frequency and time synchronization, and also to transmit the control messages on the forward link only and not on the reverse link. Okay, all the fields that I have already explained in the previous format. And the next one is your random access channel, that is RACH burst, random access channel burst. And this channel burst, it is used by mobile station to access services from any base station. So this is used by mobile station to access services from any base station. Basically what happens is, actually normal burst that we use for the data transmission, and after the data transmission starts, this random access channel is assigned, which is there to access the services from the base station or any base station which is desired by the mobile station, that is from where it is getting the signal strength. Okay, and the format of this particular burst is like this. Here instead of 3 bits you have 8 bits, and these are your start bits. Then you have 41 bits, which are your syncing bits or synchronization purpose. After that you have 36 bits, these are your bits reserved for encrypted data. Then you have 3 bits, and these are your stop bits. And finally here you have 68.25 bits, which are reserved as your guard period. So here your guard period is extended from 8.25 bits to 68.25 bits. And this is actually used by the mobile station to access the services from any of the desired base stations. And here instead of using 3 bits, 8 bits are being used for start bits. Then you have 41 bits as synchronization bits. Then 36 bits are used for encrypted data transmission, and then 3 bits are reserved as stop bits. And here guard period is extended just to avoid the overlap between the two different time slots during the propagation. So here this is the format of this RACH burst, and this is basically a standard. And in this standard there are different categories of these data transmission, and each time slot is having its own different format where data can be transmitted, but this one is also not a preferred one. the preferred one is your normal format. So next we have to study about dummy format, which is the last one. In dummy burst, we have again 6 fields. This dummy burst is actually like your normal burst, and it has these 3 bits. These are your start bits in the first field. Then we have 58 bits. In the normal burst, this was your encrypted data, but here these 58 bits are reserved for mixed bits. Then we have 26 bits. These are reserved as your training bits. After this, we have again 58 bits. This is again your mixed bits instead of encoded data. Then we have next field of 3 bits, and this is your stop bits field. And the last one is 8.25 bits, which are reserved as your guard period. Okay, so our dummy burst is basically it is used for the unused time slot. So it is used for unused time slot. For example, if there is no user to transmit in a particular time slot, and then this dummy burst is used as an information filler just to fill that time slot. And it has different fields like the initial start bits, 3 bits, then you have stop bits and 8.25 bits. These are meant for to avoid the overlap of different time slots. And here, as I said that this is just for the information filler purpose. So here no data is transmitted, and instead of transmitting actual data, here mixed bits like this, and in this field mixed bits, that is a mix stream of zeros and ones which have no purpose, they are transmitted. And again these training bits, they allow the adaptive equalizer to analyze the characteristics of channel before decoding the data. Okay, so this is basically to fill that particular time slot where we do not have a particular user to transmit. So this is all about these different formats or these different burst categories which are used for data transmission or control signal transmission in GSM technology. And now in general we have to see the time slot, the frame, the multi-frame, and the superframe concept in GSM. Okay, so till now we have studied about time slot. So I will draw the one time slot here. This represents your one time slot, and by combining 8 different time slots we get frame. And after that, by combining 26 frames we get multi-frame, and then by combining 51 multi-frames we get superframe, and again by combining 2048 superframes we get a hyperframe. So let me draw the diagram first. Okay, this is basically the complete GSM frame format, and here you see from the bottom we will start. And in the bottom you can see there is a one single time slot, and this time slot has 8 different fields, and 3 are here and 3 bits here. These are your tail bits. Initially we have studied about these bits as start and stop bits. So here we are representing these 6 bits as tail bits, and the purpose of these tail bits is to Again, I will repeat that to avoid the overlap between different time slots while in the transmission. Then we have 57 bits of coded data, and again 57 bits of coded data here. And in the previous burst formats, we have seen that in normal burst we have 58 bits, but their 58 bits include this single bit as well. And here this single bit is representing a stealing flag, and this stealing flag tells whether the transmission is a control information or the actual payload transmission. So this stealing flag is meant for that purpose. And here these 26 bits, they are denoted as mid-amble, and basically these are the training bits, and this allows the adaptive equalizer to analyze the radio channel characteristics. Okay, if there is any distortion or attenuation in the channel, then that is represented by these 26 bits. Fine. Okay, now we see that by combining 8 different time slots, we get a frame. And also I must tell you that the time period for the one time slot transmission is 576.92 microseconds, or 0.577 milliseconds is the time that is taken by this one time slot for the data transmission. And by combining 8 different time slots, we get a frame. And the time duration for a frame transmission is 4.615 milliseconds. And by combining 26 different frames, we get a multi-frame. And the time duration for transmission of a multi-frame is 120 milliseconds. And by combining 51 multi-frames, we get a super frame. And the super frame transmission time is 6.12 seconds. So this much time is taken by a super frame for its transmission. And by combining 2048 super frame, we get a hyper frame. Okay, so this is the hierarchy of GSM frame structure. And we know that in one time slot 156.25 bits are transmitted, and also the rate is given as 270.8333 kb per second. In this transmission, we see that instead of 116 bits of information transmission, we are transmitting 114, that is 57 plus 57 bits are transmitted. Now, suppose we have a system which is using GSM technology, and if that system is using normal burst, if a system is using normal burst, and in normal burst, what we see that there are 6 bits. These are start and stop bits. We have 8.25 bits as guard period bits. We have 26 bits. These are your training bits. Okay, and all these different fields, these are the 3 fields. This is not the actual transmission. This is basically an overhead to the transmission. This is overhead, and this cannot be your actual payload. So the actual payload in normal burst is your 58 plus 58 bits, that is equal to 116 bits. So efficiency of a frame in GSM is given by, like, we are transmitting 156.25 bits in one time slot, and a frame is constituted by 8 different time slots, so we have to multiply it with 8, and we will get 1250 bits. 1250 bits are transmitted per frame. Okay, and out of these 1250 bits, we have some overhead as well. So overhead is in one time slot is given here. This is your overhead, and you have 26 and 6, that is 32, and 8, that is 40.25 are your overhead bits. Overhead bits per time slot, and these overhead bits per frame are given as 40.25 into 8. This will give you 322, and in actual sense the payload transmitted per frame equal to 1250 minus 322, which is equal to 928 928 bits per frame. And now when we have to find the efficiency of a frame, efficiency is given by 928 divided by 1250, that is the total transmitted bits, into 100. And after solving this we will get 74.24. 74.24% is the efficiency of a frame. So this is all about the frame format. Thank you for watching this lecture.